So here we're given this octagon, and A and E are opposite vertices of this octagon. And they tell us that a frog starts jumping from this vertex to E, and then it can go back and forth anytime. So it could go this, come back, then go forward, forward, back, and then once it reaches E, it stops. So the question is, if AN is the number of distinct paths of exactly n jumps ending in E, so for example, if the frog were to just make it directly to E, that would be 4 jumps. So n here is 4. And then the question is, how many distinct paths can be exactly 4 jumps? So there's only 2. One is going this way, one is the other way. So A sub 4 is 2. So that's just a special case. Now they're looking for A sub 2n minus 1. And the key thing to note is that 2n minus 1 is always odd. So we're looking for how many distinct paths are there from A to E that involves an odd number of jumps. And we can actually use an example here. So for example, if n is 4, this would be A sub 7. So how many paths are there so that the frog reaches from A to E in 7 jumps? That's what we need to find. Now the key thing is that it takes 4 jumps to reach directly to E, and anytime, let's say you're at H and then you go back to A and then you come back to H, that's an increment of 2 jumps. So that would, and then if you continue straight to E, that would be a total of 6. So the key is that anytime you're at a certain vertex and you go back, let's say even if you go from G to H to A and then back, you're actually only adding an even number of additional jumps. So because it's only 4 jumps directly to E from A to E, the only way you can reach E is to have an even number of jumps. So actually, it's not possible to reach from A to E in 7 jumps, which means that the number of distinct paths to reach from A to E in an odd number of jumps is actually 0. So the answer is 0, which is choice A. So you could, I think in the exam conditions, you could just look at, try to create different paths with 7 jumps, and you'll find there isn't any. And you could just use that. Now, just to kind of end this problem, this is actually copied from a International Math Olympiad 1979. It is a hard problem, obviously. But of course, in that particular, you'll notice that it's the exact same problem. There, they were asking you to not only prove that the number of distinct paths to reach from A to E in an odd number of jumps is 0, but they also want you to find the general case, the number of distinct paths for n jumps. And you can check this, that if n was 2, which would be A sub 4, which is the case, and if you substitute that, that does indeed come out to be 2. So, but this is obviously a much harder problem, but that's where this particular problem has been copied. So to summarize, the answer is A.